All right, let's have a look at practice quiz number 12. Question number 1 says, the minimum permissible mass of an F1 race car is 702 kilograms, including the driver. In other words, every car, including the driver, has to have a mass that's bigger than 702 kilograms. We've got a 702 kilogram race car. It's accelerating from 90 kilometers per hour to 252 kilometers per hour. We're going to draw attention to this so we don't forget to convert that to meters per second. Now let's write down some givens here. We've got a mass here of, in this particular car, the minimum possible mass is the mass of this car. It's 702 kilograms. We're going to say our initial speed is 25 meters per second. That's really 90 kilometers per hour. Multiply that by 1,000 to get meters. Divide by 3,600 to get seconds, right? 25 meters per second. VF, 252 times 1,000 divided by 3,600 gives me 70 meters per second. And my time interval here is 2.00 seconds. Now, in question A, I'm only looking for the work, but we know that in question B, I'm looking for the power. So I'm just going to write that down now as well. Now, I've got two options for finding work. We know we're allowed to use W is equal to F times D times cosine theta, if there is a theta, which there's not here. Doesn't look like I have an F or a D either, though. So I think I'm going to abandon that method and try option number 2, which remember is the work energy theorem. W is equal to delta E, the change in energy. The final minus the initial energy. Now this car is accelerating from a certain speed to a faster speed. So it's got kinetic energy as both the final energy and the initial energy. We're going to say 1F mvf squared, final energy, minus 1F mvi squared, the initial energy. Now let's sub some numbers in here. We've got 1/2 times the mass. The mass does not cancel here. It's in every term on the right-hand side, but it does not appear on the left-hand side. So we can't cancel it. Here's the final energy minus the initial energy, 1/2 of 702 times 25 squared. Don't forget to square that speed. Fairly common mistake, forgetting to square that speed for both the initial and the final speed. We calculate that, we're going to end up with a value of 1500525 joules. Now we're going to round that to 3 significant digits. The 4th digit is a 0, so we're going to round that down. 1.50 times 10 to the 1, 2, 3, 4, 5, 6. 1.50 times 10 to the 6 joules is our work done by this car. Now, we've talked about this before. Whenever we're looking for power, it's an easy question now, right? Once we have work done, power is easy. We just take the work and divide it by the time. So my work here is 150.0525. We always want to use our unrounded number if we're carrying it forward for another question. Divide it by 2.00 seconds, my time interval here, and that gives me 750.262.5 joules per second, or watts. And once again, we're going to round that to 3 digits. The 4th digit is a 2, so the 3rd digit rounds down to 7.50 times 10 to the 1, 2, 3, 4, 5. 7.50 times 10 to the 5 watts. Question 2 says a 250-gram ball is thrown at a speed of 20 meters per second, an angle of 40 degrees from the top of a 50-meter high hill. How fast is it going when it's halfway down to the ground? Now, if I was doing this as a projectile motion question like I did back in our last unit, that angle would matter. But if I'm treating this as a conservation of energy problem like I am in this unit, then that angle doesn't matter because energy is a scalar, speed's a scalar. The direction's irrelevant. Now, because I'm only looking for the final speed as opposed to the direction of the final velocity, we can do conservation of energy. Let's write down some givens here. Let's say m is equal to, we're going to convert that grams to kilograms, 0.250 kilograms. My VI, as I throw the ball, it's 20 meters per second. My HI is 50 meters. My HF, this is the final height. When it's halfway down to the ground, it's 25 meters. And we're going to solve for VF here. EI equals EF. The initial energy equals the final energy. Now, what kind of energy do we have at the beginning of this problem? Well, it's moving, right? The ball's moving, so it's got kinetic energy. 1F mvi squared, plus it's got a height, so it's got potential energy as the ball is thrown from this 50-meter high cliff. Now, at the end of the problem, we're looking for the speed halfway down, so it's got kinetic energy. In fact, it's got more kinetic energy than it started with, plus potential energy, because it's still got a height of 25 meters. I'm going to sub some numbers in here. When I did my answer key, I actually missed crossing off the m's, canceling out the masses. We can do that, right? Because mass appears in every term. But because my answer key doesn't have that, I'm going to just sub in the masses here. If you cancel the masses, that's fine. You should get the same answer. There's the initial energy equals the final energy, 1/2 of the mass. And we're solving for VF there. And this is the final potential energy. And again, you could have canceled out the mass there. I just missed that when I was doing my answer key. Let's calculate this one together since it's a little bit of an icky one. I think I want to calculate this side and this term and then combine those. So let's do the left side first here. Let's say bracket 0.5 times 0.25 times 20 squared, and that first bracket, plus bracket 0.25 times 9.81 times 50, and that second bracket. On the left-hand side here, I'm going to get 172.625. Then I actually said 1/2 of 0.25 is 0.125. And then I calculated 0.25 times 9.81 times 25, and I got 61.3125. Now it's a little bit simpler here. Now let's take this term over to the other side by subtracting. Remember, we got to get rid of what's not attached first. So 172 minus 61 gives me 111.3125 equals 0.125 times VF squared. Let's take the 0.125 over by dividing, and then let's square root. So divide by 0.125, then square root, and we should get a VF here of 29.84 meters per second. We're going to round that to 2 digits. The third digit is an 8, so the second digit is going to round up. That gives me 30 meters per second. That seems reasonable, right? We started at a speed of 20 meters per second. Now halfway down, we're moving at 30 meters per second, faster than we were when we started. Now question B, when it reaches the ground, we should expect a speed that's even more than 30 meters per second. We're going to say EI equals EF, 1/2 mvi squared plus mgh. The initial energy is just going to be the same, isn't it? But the final energy, when we reach the bottom, is only going to be kinetic, because of course when you reach the ground, there is no height, there is no potential energy. Now, I'm going to cheat here a little bit. I already calculated that initial energy. I got 172.625 equals 1/2 of the mass of 0.25 times VF squared. Now I'm going to actually calculate this one. We're going to say 172.625. I'm going to times that by 2, or I could have divided it by 0.5 or 1/2. Let's divide that by 0.25. Press enter. 1381. And now I'm going to take the square root of that. And I should get 37.16 meters per second. We want to round that again to 2 digits. Sorry, that's not a vector. We're talking about speed there, not velocity. rounded to 2 digits. The second digit should round down. Should get 37 meters per second per now. That's it.